Welcome to your quiet corner of cosmic discovery. I'm here to share something genuinely fascinating about our universe at just the right volume for drifting off. You know what's been on my mind lately? The idea of building an elevator that stretches all the way into space, or even reaches the moon. There's something remarkable about imagining a gentle ride upward instead of a roaring rocket, and I can't wait to share what makes this dream both wild and surprisingly possible. Your support through likes and subscriptions keeps this tranquil laboratory of knowledge glowing softly. Tell me in the comments, what scientific concept has always fascinated you? First, let's create the perfect space for learning. Cocoon yourself in comfort, release any lingering tension, and let your breath become soft and steady. Close your eyes if you wish, and allow your mind to drift far above the earth, where the sky deepens from cerulean blue to the midnight black of the cosmos. There, in that liminal space where atmosphere gives way to vacuum, humanity's oldest dreams come to rest against the cold, silent stars. For as long as humans have looked up, they have wondered, what would it be like to touch the sky? What would it mean to reach beyond, to climb, not merely through the air on wings, but upwards, ever upwards, until the world itself falls away beneath one's feet. The longing to ascend is woven deep into the stories of every culture. In the myths of ancient China, a goddess named Chang'e floated serenely to the moon, her silhouette forever outlined there, a distant companion to those who gaze up on autumn nights. The Tower of Babel, rising from the cradle of Mesopotamia, was said to scrape the very heavens, an audacious monument to human ambition, halted only by divine intervention. In the Andes, the Incas told stories of Viracocha, who walked the path of the sun, while the Aboriginal Australians spun tales of the sky world, a realm accessible only to those who followed the sacred tree, whose roots and branches stretched between the worlds. Across centuries and continents, the motif repeats, a yearning to bridge the divide between earth and sky, to build a stairway, a ladder, a bridge, a beanstalk, a thread, reaching upward into the stars. As generations passed and knowledge grew, the dream persisted, reshaping itself to fit each new era's understanding. In the age of sail, when the globe itself seemed vast and mysterious, the notion of reaching even the highest mountaintop was adventure enough. But soon the hot air balloon, then the airplane, and finally the rocket, each in their time, rendered the sky less an impenetrable vault and more a threshold to be crossed. Yet even as Apollo's mighty Saturn V thundered skyward, casting 3 men and their fragile vessel outward toward the moon, a new question began to form. Was there perhaps a gentler way, a method not of brute force and roaring fire, but of patience and persistence, a way to climb step by step from the ground to the stars? It is here, in the fertile ground between myth and mathematics, that the idea of the space elevator took root. To trace its origins, let us journey not merely through space, but through time, back to the early 20th century. The Russian scientist and visionary Konstantin Tsiolkovsky, whose mind was as boundless as the universe he sought to understand, was among the first to give form to the ancient dream. Inspired by the monumental spire of the Eiffel Tower, Tsiolkovsky imagined a structure that would soar ever upward, its base anchored securely to the earth, its summit reaching out into the endless night. He envisioned a tower so tall that its tip would brush the realm of geostationary orbit, some 35,786 kilometers above the equator, where an object could circle the Earth at exactly the same rate as the planet turns. There, he reasoned, one could step from the ground into a waiting vessel and ascend, not with the violence of chemical rockets, but with the steady, unceasing pull of mechanical power. At first, this idea seemed to belong more to the realm of fantasy than science. To build a tower so tall, so slender, and yet so strong would require materials unknown to the world of Tsiolkovsky's day, substances capable of withstanding unimaginable stresses, of defying gravity's relentless tug. For decades the notion lingered on the margins of scientific thought, half dream and half theory, an impossibility awaiting its hour. But the space elevator would not remain confined to the shadows. In the late 20th century, the dream caught the imagination of writers and creators who saw in it not merely a technical challenge, but a symbol, a metaphor for hope, for ambition, for the eternal human thirst to transcend boundaries. Among these visionaries was Arthur C. Clarke, whose novel The Fountains of Paradise stands as perhaps the most iconic literary exploration of the space elevator concept. In Clarke's story, the mountaintop kingdom of Taprobane, a thinly disguised Sri Lanka, becomes the birthplace of an endeavor so grand that even the gods might pause to marvel. An engineer, Vannevar Morgan, is driven by the vision of linking the earth and heavens with a slender thread, a cable stretching from the ground to a satellite in geostationary orbit. The project is fraught with peril, not only the dangers of engineering, but the resistance of tradition, the inertia of politics, and the unpredictable whims of nature herself. Yet through it all, Clarke's narrative pulses with a quiet optimism, the conviction that given enough time and ingenuity, humanity might one day rise above its limitations, not by brute force alone, but by the elegance of an idea whose time has come. Clarke's depiction is meticulous in its detail, and yet infused with a sense of wonder. The elevator, when completed, is not merely a machine, but a new axis mundi, a pillar connecting earth and sky, science and spirituality, past and future. In the climactic scenes, a climber ascends through bands of cloud and weather, past the realm of birds and storms, into the thin blue hush where the curvature of the earth becomes visible. Here, the machinery of the elevator becomes a kind of magical realism, a technological beanstalk, echoing the fairy tales of Jack and his ascent to the land of giants. This literary vision resonated far beyond the pages of Clarke's novel. The space elevator found new life in the world of visual storytelling, especially in the vibrant narratives of Japanese anime and manga. In Mobile Suit Gundam, for instance, the space elevator is reimagined as a towering structure at the heart of political intrigue and philosophical struggle. The elevator becomes both a strategic asset and a symbol. Its presence, a silent reminder of the precarious balance between earth and sky, peace and conflict, old worlds and new. In these stories, the elevator is more than a backdrop. It is a character in its own right. Its construction provokes awe and anxiety alike. Societies gather around its base, their fortunes rising and falling with the tides of commerce and innovation the elevator enables. It is both mundane and miraculous, a piece of infrastructure as familiar as a bridge or highway, yet as audacious as the first leap into orbit. Through its cables flow not merely passengers and cargo, but the dreams and fears of entire civilizations. This motif is not limited to anime alone. Across the spectrum of speculative fiction, from the techno-utopian visions of hard science writers to the lush, painterly worlds of animation, the elevator recurs as a totem of possibility. Sometimes it is rendered in dazzling detail, the carbon nanofiber cable, thinner than a hair, yet stronger than steel. The climbers, powered by solar arrays or magnetic induction, gliding silently upward. The stations and harbors suspended in the sky, bustling with travelers bound for the moon, Mars, or beyond. At other times the elevator is mysterious, half seen in the mist, a silhouette against the dawn, its top lost in the clouds. Yet while fiction weaves tales of triumph and tragedy around the elevator, science quietly inches forward, measuring, testing, dreaming in its own way. The basic concept is elegant, almost deceptively so. Imagine a cable anchored at the equator, reaching straight up to geostationary orbit. At that altitude, the centrifugal force of the Earth's rotation would balance the pull of gravity, allowing the cable to hang taut, neither falling to Earth nor flying off into space. Along this cable, climbers could ascend or descend, carrying payloads far more cheaply and safely than the roaring, explosive drama of rockets could ever allow. The technical challenges, of course, are immense. The cable must be unimaginably strong, yet impossibly light. It must withstand wind, weather, radiation, micrometeoroids, and the constant flexing of the Earth itself. No known material, not even the strongest steel or the most advanced polymers, could bear such a burden, at least not yet. Scientists and engineers pin their hopes on the marvels of nanotechnology. Carbon nanotubes, graphene ribbons, materials whose strength is measured in the bonds of atoms themselves. Should these materials ever be manufactured in sufficient quantity and flawless length, the dream might flicker into reality. But even as the science advances, the space elevator remains a canvas for speculation, a mirror for our deepest hopes and anxieties. In every depiction, from Clarke's painstakingly detailed blueprints to the soaring, impossible silhouettes of animation, the elevator stands as a testament to a paradox. The tension between gravity and aspiration, the earthbound and the starbound, the limits of what is and the lure of what might be. There is something inherently poetic in the image of a tether stretching from the ground to the heavens, It calls to mind the ancient stories, the silken ladder of the gods, the vine that Jack climbed, the stairway of Babel. Yet it is also unmistakably modern, a product of our own age's peculiar blend of audacity and precision. To build a space elevator would be to inscribe a new myth upon the world, a story not of magic or divine intervention, but of human ingenuity, persistence, and longing. Consider for a moment the societies of the future gathered in the shadow of the elevator's base. Imagine the marketplaces, the ports, the cities that might grow up around such a marvel. Children would point upward, their questions mingling with the laughter of tourists and the hum of industry. Pilgrims might come from distant lands to stand at the foot of the great cable and ponder the journey of ascent. For some, the elevator would be a gateway to opportunity, a means to travel, to trade, to learn. For others, it might be a symbol of hubris, a reminder of the dangers of overreaching. Yet for all, it would be a wonder, a physical link between the world as it is and the universe as it might one day be. This is the promise and the peril of the space elevator, that in seeking to rise, we are forced to confront the limits of our own knowledge and courage. Each attempt to climb higher, whether in fiction, in myth, or in the laboratories of today, brings with it the echo of Babel's unfinished tower, the memory of Icarus's wings. Yet it is precisely these echoes that make the dream so compelling. As night deepens and the stars wheel overhead, one might find comfort in the thought that humanity's longing to ascend is as old as consciousness itself. From the first campfires to the glowing lights of orbiting satellites, from the stories whispered beneath constellations to the blueprints drawn on laboratory tables, the dream persists. The space elevator is, in a sense, a crystallization of that very yearning, a ladder not only for the body, but for the mind. In the silence of the early hours, as the world sleeps and the sky turns slowly above, the image lingers, a cable impossibly slender, reaching from the earth into the uncharted dark. Somewhere far above, the first climber begins their ascent, rising slowly through layer after layer of cloud and cold, leaving behind the familiar for the unknown. Below, the world waits, wondering, hoping, daring once again to believe that the impossible might, with patience and courage, become real. And so the story continues, the dream unfolding, each new attempt and each new vision building on the last. The stars remain distant, but perhaps not forever. The elevator, whether of steel or of story, reaches upward still, its promise as yet unfulfilled, its cable taut with possibility. The night is long, but the dawn will come, and with it new hopes, new questions, and new paths to the sky. The world outside is quiet, and the mind begins to drift upwards, tracing the dream of a ribbon of matter, anchored to the earth and stretching far beyond the clouds into the velvet blackness of space. This is the space elevator, a vision as audacious as any conjured in the long, drowsy nights of human imagination. Yet, as with all great dreams, the details are where the gravity of the situation reveals itself, both literally and figuratively. Let us start at the first principle, the one that binds us all to the earth, gravity. Its invisible hand is gentle enough to allow a leaf to fall softly, and yet so persistent that it shackles every mountain, every ocean, every molecule to the planet's surface. To break free of this embrace, to send anything, be it a rocket, a pebble, or a hopeful human, into orbit, requires a tremendous burst of energy. The space elevator, in its elegance, promises a gentler ascent, not an explosive leap, but a patient climb. But this apparent grace is an illusion, for gravity's grip does not fade easily. The cable itself is the heart of the elevator. Imagine it, a strand thinner than a bridge cable, yet mightier than any steel spiderweb we have ever spun, rising from the equator and stretching some 36,000 kilometers upward, reaching geostationary orbit, the place in the sky where a satellite circles the Earth once every 24 hours, always hovering over the same point on the surface. At this altitude, the centrifugal force from the Earth's rotation balances the pull of gravity. It is here that the elevator's cable can be tethered, taut as a bowstring between the spinning planet and the outward pull of the heavens. Yet the cable cannot stop at geostationary orbit. Beyond this point, the ribbon must continue, for if it ended there, the entire structure would simply collapse back toward Earth, like a snapped kite string falling from the sky. To hold the cable aloft, a counterweight is needed, a mass, perhaps a decommissioned asteroid, or a cluster of spent rocket stages, stationed thousands of kilometers higher still, pulling the cable outward through the inertia of its own motion. The cable, therefore, is not just a bridge from ground to sky, but a tightrope stretched between the pull of the Earth and the centrifugal force of the spinning world. Consider now the material required for such a feat. Every meter of cable, from the ground to the counterweight, bears the weight of all the cable below it. At the surface, the load is immense. The entire structure hangs from this anchor point, and the force grows with every kilometer of altitude, peaking at geostationary orbit. The material must be unimaginably strong, far beyond steel or even the finest synthetic fibers that our civilization has woven. The figures are daunting. To support its own weight, the cable must have a tensile strength-to-density ratio that outstrips the best metals by orders of magnitude. For decades, this challenge seemed insurmountable. No known substance could survive the strain. Then came the discovery of carbon nanotubes, cylinders of pure carbon, only nanometers across yet stronger than any material previously encountered, with the potential to make the dream plausible. In theory, a cable spun from such threads could bear its own weight to geostationary orbit and beyond. But reality, as always, lags behind theory. While carbon nanotubes can be grown in laboratories, assembling them into flawless kilometer-long strands, let alone a cable stretching tens of thousands of kilometers, is a task that still eludes us. Each imperfection, each tiny flaw, becomes a potential point of catastrophic failure, and this is only the beginning. The cable must brave the hostility of near-Earth space, the battering of micrometeoroids, the unrelenting ultraviolet light, the corrosive ions of the upper atmosphere. Even a single, unseen impact could fray the cable, sending vibrations shuddering down its length, threatening to unravel the entire structure. Maintenance, too, becomes a monumental challenge. How do you inspect and repair a thread that crosses half the distance to the moon, swaying gently in the tides of air and magnetic field? The elevator must be more than a cable. It must be a living, self-healing structure, able to sense and mend its wounds. The question of energy, too, looms large. To climb the elevator is no small feat. A payload lifted from the ground to geostationary orbit must still gain the same energy as a rocket launched into space. The difference is in how the energy is supplied. Rockets carry their fuel with them, expending it in a furious burst that leaves behind a trail of flame and exhaust. An elevator car, by contrast, draws its energy from external sources, perhaps beaming it up from the ground via powerful lasers, or drawing electricity from a ribbon of conductive material woven into the cable. The total energy cost is dictated by physics, not by engineering whim. To reach geostationary orbit, a mass must gain both altitude and the velocity required to circle the Earth at 3 kilometers per second. The elevator's climb would be slow, hours or even days, as opposed to the frantic minutes of a rocket launch. But the sum total of energy remains the same, bound by the immutable laws of the universe. There are no shortcuts. The work must be done. And what of the myth, the old alluring notion of simply climbing to the moon? It is a pleasing fantasy, one that has crept into many a tale and textbook. Yet the moon is not a fixed point in the sky, waiting at the end of a cosmic ladder. It circles the Earth on its own path, dancing to the tune of gravity and orbital mechanics. The space elevator is anchored to the Earth, spinning with the planet's rotation. Its cable, if extended far enough, would not lead to the moon, but would instead sweep out in a vast, ever-widening arc, tracing the equator in the sky. To journey to the moon, one must first reach space, then embark on a separate voyage, timed to intercept the moon's orbit. The elevator delivers you to the doorstep of space, but from there the journey becomes a new adventure entirely. The harsh realities of space travel are revealed in the interplay of forces and energies, the ever-present risk of failure, the ceaseless demands of maintenance and vigilance. The sun in space is not softened by the atmosphere. Its light is searing, its radiation unforgiving. The vacuum is absolute, a realm where air and water and warmth must be supplied with infinite care. Each meter of the elevator's cable is exposed to these extremes, and every payload, every human traveler must be shielded from the silent dangers. The challenges grow steeper the higher you climb. At low altitudes, the air is thick, the wind unpredictable, the threat of storms and lightning ever present. Here the cable must be anchored to a platform, perhaps at sea, drifting gently with the currents to avoid the fiercest hurricanes, or perhaps on land, armored against the shifting crust and the restless weather. Elevator cars must pass through this turbulent zone, rising above the clouds into the rarefied air where only the boldest aircraft dare to fly. Beyond the atmosphere, the hazards change. Micrometeoroids, fragments of ancient collisions, race through the darkness at tens of kilometers per second. The smallest pebble can punch a hole through metal, slice through cable. The elevator becomes the world's longest target, exposed to the debris of ages. Protective shielding, early warning systems, and perhaps even robotic repair drones must become part of its anatomy. There is also the matter of oscillation. The cable is not a rigid rod, but a flexible ribbon, subject to the whims of wind and weather, of thermal expansion and contraction, of the slow push and pull of the moon's gravity. Resonances can build, waves can ripple up and down the length, amplifying until the structure shudders and threatens to snap. The dance of physics is intricate, and human engineering must choreograph it with care, damping vibrations, anticipating the unpredictable. And so the space elevator emerges not as a simple ladder to the stars, but as a symphony of challenges, materials and mechanics, energy and environment, all balanced on the fine edge between what is possible and what is yet beyond our reach. The limits of our knowledge, too, are laid bare. We know, in theory, how to design cables of titanic strength, but the practicalities of manufacturing them at scale remain daunting. We understand the orbital mechanics that would allow a counterweight to balance the system, but the logistics of assembling such a structure in space are staggering. There is the uncharted territory of materials science, the hope that graphene or some undiscovered supermaterial might one day tip the balance. There is the ever-present risk of sabotage, of collision, of unforeseen disaster. Yet, even as we confront these realities, the dream persists. For every obstacle, there is a spark of ingenuity, a hint that human curiosity and determination may one day find a way. Perhaps it will not be a single ribbon, but a network of cables sharing the load. Perhaps the elevator will be built on another world first, on the lesser gravity of Mars or the airless bulk of the Moon, a proving ground for the technologies we dare not test on Earth. In the quiet hours, as the mind drifts upward along the imagined cable, one can feel both the weight of the challenge and the lightness of possibility. The elevator is both a monument to our limitations and a beacon of our potential, suspended between the certainty of gravity and the promise of the stars. And so the story remains unresolved, the dream lingering just beyond reach, like the glint of sunlight on a distant cable swaying gently above the world. There is more to be explored, the promise of what such a structure could bring, the worlds it might open, the new chapters it might write in the long, slow story of human ascent. But for now, let the mind rest in the quiet tension of the cable, feeling the pull of the earth and the draw of the infinite suspended between what is and what might yet be. Under the hush of laboratory lights, in the quiet hours when most of the world slumbers, a peculiar kind of magic stirs. It is not the magic of wands or incantations, but the patient sorcery of equations and materials, of minds working at the edge of the possible. Here the dream of the space elevator is not merely a flight of fancy, nor a vision confined to the pages of science fiction. It becomes instead a question posed to the universe. Can human ingenuity coax from the raw stuff of the earth a bridge to the stars? To begin to answer this, let us travel in imagination to the heart of a modern laboratory, where the air smells faintly of ozone and the hum of delicate machinery is the only music. Here, under the lens of a microscope, a scientist is threading a needle, not of steel and thread, but of carbon atoms arranged in a lattice so precise it challenges the imagination. Her hands are steady, though her eyes ache from hours of focus. She is assembling carbon nanotubes, those miraculous cylinders whose walls are a single atom thick, yet whose strength may one day anchor humanity's most audacious construction. Carbon nanotubes are a material that seems almost designed for dreams such as this. Their strength is legendary, 100 times that of steel, yet as light as a feather's memory. Their secret lies in the peculiar chemistry of carbon, whose atoms can link in endless hexagonal tessellations, rolling themselves into tubes with diameters measured in billionths of a meter. It is in these infinitesimal structures that the hope of a space elevator is cradled, because to stretch a cable from the surface of the Earth to geostationary orbit is to demand a material that can bear its own weight for more than 35,000 kilometers. No substance forged thus far by human hands has met that test. But here, in these tiny tubes, the equations begin to whisper yes. The scientist, let us call her Dr. Sato, works with a focus that excludes all else. She has spent years coaxing carbon atoms to assemble as she wishes, adjusting the temperature of chemical vapors, the flow of gases, the subtle influences of catalysts. Each step is a careful negotiation between theory and reality. She knows, as all material scientists do, that nature is both generous and capricious. What works in the neat confines of a pencil sketch may unravel in the rougher world of molecules. Still, she persists. In her notebook, a spidery hand records each triumph and setback. Here a nanotube grew to a few centimeters before snapping. There, a new catalyst yielded a bundle so pure and aligned that it gleamed silver under the electron beam. Her work is not solitary. She is part of a tapestry of researchers scattered across continents, each contributing a thread to the growing weave. Yet in these late hours, the labor feels personal, almost intimate, a conversation between her mind and the matter beneath her fingertips. Elsewhere, in a windowless room aglow with the blue light of computer screens, an engineer named Ravi loses himself in calculations. He is the sort of person whose friends tease him for carrying slide rules into the age of supercomputers, for scribbling equations on napkins or the backs of train tickets. But tonight, as the world outside is muffled by rain, it is his mind that ranges farthest, reaching for answers to questions that have not yet been asked. The mathematics of the space elevator are profound and unforgiving. Ravi runs simulations that model the stresses a cable would endure, the crushing weight at its base, the subtle tug of tidal forces, the relentless assault of micrometeoroids and radiation. He must account for winds that swirl across the stratosphere, for the looping orbits of satellites, for the minute expansion and contraction of materials as they warm in the day and chill in the night. Each variable is a potential flaw, a thread that could unravel the entire tapestry. Tonight's problem is a subtle one: how to taper the cable so that it is thickest where the stresses are greatest and thinnest where gravity's grip loosens. The mathematics are elegant, a dance of exponential curves, but the real world is always more complicated than the blackboard's promise. Ravi's model suggests a solution, but it requires a material whose strength exceeds even that of the best-known carbon nanotube fibers. He sighs, rubs his eyes, and returns to his calculations, undaunted. If the laws of physics cannot be changed, perhaps the cleverness of engineers can find a loophole, a way to braid many weaker fibers into a composite stronger than its parts, or to shield the cable from the hazards of the upper atmosphere. In a smaller, quieter room, little more than a closet lined with battered equipment, a graduate student named Amara conducts an experiment that seems almost quaint in its simplicity. She has built a miniature elevator, a spool of thread, a tiny motor, a plastic bead as payload. Her goal is to study how vibrations travel up and down a long, thin line. When the motor whirs, the bead shudders and a ripple runs up the thread. Amara watches this wave, recording it with a high-speed camera, and later analyzes the data for clues. If a real space elevator cable should begin to oscillate, set into motion by winds or passing debris, how might those vibrations grow? How might they be damped before they become catastrophic? Amara's work is humble but essential. It is one thing to imagine a cable hanging serene above the earth, quite another to manage the wild energies that nature is always ready to unleash. In her notebook, she sketches graphs, amplitudes rising and falling, frequencies shifting with the length and tension of the thread. She dreams, as all experimentalists do, of scaling up, of seeing her modest thread replaced by kilometers of carbon nanotube ribbon, of watching as real climbers ascend into the upper atmosphere. For now, she contents herself with the data and with the knowledge that each small answer builds toward something grander. In the world outside these laboratories, the pursuit of the space elevator draws in minds from many disciplines. Some are chemists, seeking ever purer forms of graphene or other two-dimensional materials, hoping to surpass even the remarkable properties of carbon nanotubes. Others are roboticists, tasked with designing climbers, machines that can grip and crawl their way up the cable, carrying cargo and perhaps one day people. They test prototypes on vertical tracks, on long wires suspended from radio masts, pushing their creations to move ever faster, to carry ever greater weights, to repair themselves in the face of damage. There are atmospheric scientists, too, who map the winds and weather that swirl around the equator where the elevator must be anchored. They launch weather balloons, monitor satellites, and build computer models that trace the paths of hurricanes and typhoons. Their data will help determine whether a cable can survive the tempests of the lower atmosphere, or if some clever shield or guidance system is needed to nudge the structure away from danger. Meanwhile, in the quiet offices of mathematicians, new algorithms are born. These are the minds who ponder how to control a cable thousands of kilometers long, swaying gently in the gravitational tides. They devise feedback systems, networks of sensors and motors that could detect the smallest tremor, the slightest deviation, and respond in real time to keep the ribbon taut and true. Their equations lace through the design like unseen stitches, holding everything together. And then there are the dreamers, artists, writers, visionaries, who help to keep the flame alive, who sketch the elevator rising into the sky with the delicacy of a dragonfly's wing, who remind us why we strive for such wonders in the first place. All these efforts, scattered across the globe, are bound by a common thread, the belief that the difficult is not the same as the impossible. Progress is measured in increments, a nanometer longer fiber, a slightly stronger composite, a simulation that runs a little closer to reality. There are setbacks too, a batch of fibers that fracture at half the expected load, a climber that stutters and fails, an experiment whose results stubbornly refuse to match the theory. In these moments, the pursuit of the space elevator can feel quixotic, even futile. Yet perseverance is its own quiet triumph. If you were to walk through these laboratories and watch these minds at work, you would see more than just technical skill. You would witness the slow, patient artistry of science, the willingness to try and fail, to learn from each misstep, to return again and again to the problem with new eyes. You would see hands steady under the microscope, eyes bright with the reflected glow of computer screens, notebooks filled with the scribbled evidence of sleepless nights. You would hear, in the low murmur of conversation or the solitary mutterings of a late-night experimenter, the age-old refrain of those who build, "What if? Why not?" Each new discovery, each small advance is a brick in the invisible road that leads from dream to reality. The cable, still only theoretical, begins to take shape in the collective imagination, not as a single ribbon, but as a symphony of parts, the anchor, the climbers, the power systems, the safety mechanisms. Engineers debate whether the base should rest on land or float at sea to ride out the storms more gently. Some propose electromagnetic launchers to send climbers racing up the cable. Others imagine solar panels catching the fierce equatorial sunlight, beaming power to the machines as they ascend. The possibilities proliferate, each a solution to one more problem, each a testament to the boundless inventiveness of the human mind. Yet for all the planning, all the simulations and prototypes, there remains a sense of humility, a recognition that nature is both partner and adversary. The tallest towers ever built, the longest bridges ever stretched, are dwarfed by the scale of this undertaking. The cable must span the sky itself, must weather the harshest conditions the planet can muster. It must be not only strong, but resilient, not only stable, but adaptable. As the engineers and scientists toil, they look to the natural world for inspiration, to the spider's web, which bends but does not break, to the bamboo stalk, which sways in the wind but endures. They study the ways that living tissues repair themselves, the patterns by which trees grow tall without toppling. In every corner of nature they find lessons for their own designs. This is the poetry of engineering, a discipline that marries the rigor of mathematics with the intuition of the artist, the logic of the scientist with the imagination of the dreamer. It is a field where progress is measured in microns and megatons, where the smallest failure can inspire the greatest breakthrough. In the quest to build a space elevator, the frontier is not only physical, but mental and emotional, a test of patience, of perseverance, of hope. As night deepens outside those glowing laboratories, the work continues. Dr. Sato adjusts her microscope, chasing a defect in her latest batch of nanotubes. Ravi stretches, his mind abuzz with new approaches to the tapering problem. Amara reviews her data, imagining how her humble thread might one day become the backbone of a tower that reaches to the stars. Around the world, others join them, each contributing a tiny piece to the puzzle. The dream of the space elevator persists, not because it is easy, but because it is hard, because it asks of us our finest skills, our deepest curiosity, our most enduring courage. And as dawn approaches, and the first rays of sunlight creep through the windows, there is a sense that the story is not finished, that the next chapter awaits, a chapter in which the work of tonight may become the marvel of tomorrow, and the impossible may yet become real. Beneath the immense sweep of night, with the ocean's hush as quiet company, we gaze up at the stars as our ancestors did, centuries and centuries ago. The sky, immense and unyielding, has always been the canvas onto which our aspirations are projected. There is something deeply human in our longing to ascend, to rise above the limitations of flesh and gravity, to touch the places where the earth's blue fades into the black infinity above. The idea of a stairway, a space elevator, linking our spinning planet to the tranquil silence of orbit, is as much a testament to our yearning for transcendence as it is an engineering proposal. In this quiet hour, let us reflect on the meaning such a structure would have, not merely as steel and carbon and cable, but as an emblem of our restless quest to know and to become something more. A space elevator is, at its core, a bridge, but unlike any bridge humanity has ever built, its span is not across chasms or rivers, but across the very boundary between Earth and cosmos. Its foundation is sunk not in bedrock, but in the shared dream of reaching upward, a dream that has haunted us since the first stories were told by firelight, since the first myths of ladders to the sky and towers to the heavens. The ancient Babylonians imagined the ziggurat of Etemenanke as a stairway uniting earth and the divine. Jacob, in his vision, saw angels ascending and descending, a ladder between heaven and earth. These are not merely tales, They are echoes of the same impulse that drives our most audacious scientific projects. To build a space elevator would be to transform a universal myth into a physical reality, and in doing so to alter our conception of what is possible. If you picture it now, not merely as cable and counterweight, but as a living artery, you begin to see its deeper resonance. Along its length, rising from the surface through the cloud-wreathed sky, passing through the hush of the stratosphere, into the blazing light of the exosphere, and on to geostationary orbit and beyond, there would be a continuous flow of travelers and cargo, ideas and ambitions. The elevator would carry not just machines and materials, but the very hopes of a civilization determined to step beyond its cradle. It would not be simply a conveyor of matter, but a conveyor of meaning. What would it mean for us as a species to have such a stairway? The answer lies as much in philosophy as in science. For the first time, the wall of gravity, so absolute, so inescapable, would become permeable, traversable by any who wished to climb. The cost of reaching space would shrink, not just in money, but in danger, in exclusivity, in the sheer effort required. Today, only a handful of humans have ventured beyond the sky, borne aloft by fire and risk. A space elevator would democratize the heavens, making the act of departure as routine as a train journey, as unremarkable as a flight across continents. And with that new normalcy, a profound shift would ripple through our sense of place in the cosmos. For generations, the stars have been distant, unreachable, and yet, paradoxically, close to our hearts. They have guided navigators, inspired poets, and kindled the curiosity of scientists. Among the most striking features of human nature is our compulsion to go where we have not gone, to see what we have not seen. The first canoes pushing beyond the sight of land, the first footsteps on the Antarctic ice, the first tentative orbits above the Earth, all are part of this same story. The space elevator, then, is not merely an invention, it is a continuation of our oldest tradition, the journey into the unknown. Yet, as with every great advance, the elevator would force us to confront questions larger than technology. What do we seek when we climb? Is it resources, new metals, new energy, new homes among the asteroids? Is it knowledge, the deciphering of cosmic mysteries, the mapping of planetary frontiers, the pursuit of new sciences born in low gravity and vacuum? Or is it something less tangible, the fulfillment of a longing to be more than what we are, to escape the confines of our past and our planet, to write ourselves into the larger story of the universe? The answer, perhaps, is all of these and none. Our motivations are as layered and complex as the Earth itself. It is tempting to imagine that once the elevator is built, the flow of traffic skyward will be constant and purposeful. Supplies for orbiting habitats, components for lunar telescopes, passengers venturing to the moon and beyond. But in the stillness of the night, one senses that the most important cargo will be the changed perspective of those who ascend. For to travel slowly, steadily from the surface to the geostationary realm is to witness in a single journey the full spectrum of Earth's grandeur, the green curve of continents, the swirls of cloud, the thinness of atmosphere, the silent turning of the globe. It is to see with one's own eyes the unity of our world and its fragility. Such a journey would be a pilgrimage, not just an itinerary. And so the elevator becomes a kind of metaphor, a physical enactment of the ascent of consciousness itself. As we rise level by level, we shed the parochial, the tribal, the narrow, and begin to perceive ourselves as part of a planetary whole. The overview effect, known to astronauts who have gazed down from orbit, might become a commonplace experience. Imagine the subtle transformation in human affairs if millions could see the world from such a vantage. National boundaries would blur, ancient enmities shrink to insignificance, environmental concerns gain a new urgency. In this sense, the elevator is not just a transporter of bodies, but a catalyst for the evolution of mind and spirit. There is poetry, too, in the thought that the elevator would never truly end. Its cable, anchored to the earth, would extend out into space, past the point where gravity and centrifugal force balance, on into the trailing counterweight, perhaps a captured asteroid or an engineered mass. It would be a line drawn from the heart of the world to the threshold of the stars, a literal lifeline for a species poised on the edge of cosmic expansion. Along its length, at every altitude, there would be platforms, laboratories, habitats, observatories, points of pause, places of reflection, outposts of curiosity. Each would be a rung on the ladder of discovery. To contemplate the elevator, then, is to meditate on the nature of progress. Our advances are not always smooth or safe. The Tower of Babel fell, not from a structural flaw, but from the confusion of tongues, the lack of shared purpose. The myth warns us of the dangers of hubris, the perils of overreaching, yet it also celebrates the audacity of the builders, the courage to aspire. In our age, with its unprecedented tools and knowledge, we are called to balance ambition with humility, to reach upward without forgetting our roots in the soil and the sea. There are ethical dilemmas, too, woven into the elevator's cable. Who will own this bridge to the cosmos? Will it be a global commons, a shared heritage of all humankind, or a monopoly of the powerful? Will access be open or rationed? Will the elevator usher in a new era of cooperation or deepen existing divides? Such questions have no simple answers. They remind us that every technical achievement brings with it a host of social, political, and moral challenges. To build the elevator is also to build the society that will use it. Yet for all these uncertainties, there is a quiet faith that animates the dream of the stairway to heaven. It is the faith that by climbing higher, we become more than the sum of our parts. Each step upward is a step into the unknown, yes, but also a step toward greater understanding of the universe and of ourselves. The elevator would not only connect Earth to space, It would connect past to future, the known to the yet-to-be-known, the possible to the impossible. It would be a scaffold for the construction of new stories, new sciences, new selves. Even the act of imagining the elevator changes us. It stretches our sense of scale, of time, of consequence. We begin to see the planet as a single, finite home, and the universe as a vast, beckoning frontier. We recognize, perhaps for the first time, that our fate is not bound forever to the ground beneath our feet. We are, as Carl Sagan once said, star stuff contemplating the stars. The elevator, in its elegant sweep from equator to infinity, would be the material expression of that contemplation, a testament to the power of questions, of dreams, of the refusal to accept limits. The night deepens, and with it the silence grows more profound. Somewhere in the darkness, engineers and visionaries sketch plans, run simulations, weave carbon nanotubes in their minds. The elevator remains, for now, a possibility, a line in the sand between present and future. But even as a possibility, it exerts a gravitational pull on our imagination. It calls to us as the mountains called to Mallory, because it is there, because in some sense we are not complete until we have reached for it. And perhaps one day, when the first climber rides the elevator skyward, pressing gently upward through the layers of air and cloud and starlight, they will look back and see the earth shrinking below, a blue sphere wrapped in the thin veil of life. They will understand, in a way that words cannot capture, the unity of all things, the interconnectedness of humanity, the fragility of our home, the vastness of the cosmos that awaits. The elevator will be both a path and a mirror, revealing not just where we are going, but who we are becoming. Yet the journey is never finished. Each ascent reveals new horizons, new mysteries, new questions. The elevator may take us to orbit, to the moon, to Mars and beyond, but the true stairway to heaven is the one we climb within. Each rung a moment of insight, each platform a pause for wonder. The stars above are not merely destinations, they are invitations. The space elevator, in all its audacity, is a response to that invitation, a promise that we will not be content to remain earthbound, that we will always seek, always strive, always ascend. So let us hold that image close, a cable stretching from the green heart of the earth to the silent waiting stars. Let us dwell for a moment in the possibility it represents, a future where the boundaries of here and there, of possible and impossible, are forever changed. The night sky is not a barrier, but a beginning. The elevator is not an end, but a means to become more than we were, to know more than we have known, to love the world more deeply for having seen it from above. And as the stars wheel overhead, silent and eternal, we are reminded that our story is still unfolding, that the stairway to heaven is not a destination, but a journey, one that has only just begun. As our journey drifts gently to a close, like a comet tail fading softly into the hush of space, we are left to wonder at the shimmering possibilities of reaching beyond our world. Rest now with dreams of cosmic elevators and moonlit pathways, and return soon for more dreamtime tales that float quietly among the stars.